Today, we're going to have a very scientific and very good presentation. I've seen the slides before by Professor Milos Djukic from the University of Belgrade. He is the head of the Hydrogen Materials Interactions Laboratory. He's a member of the team for the preparation of the hydrogen strategy of the Republic of Serbia. He's an assistant subject editor for the International Journal of Hydrogen Energy. He's an executive committee member of the European Structural Integrity Society. He is the host and the moderator of the Hydrogen Embrittlement group on LinkedIn, the author of more than 100 scientific papers on hydrogen embrittlement, and certainly one of the leading experts on this very, very complex and very important topic. So, Milos, can you hear us? Are you still in the background? Welcome on stage. All right, here we go.
Yes, I am. Thank you, David.
So thank you very much for being here. I just got see a comment in the chat. I can see the chat, but no presentation. Is this correct? No, this is obviously not correct. I would assume that everybody else can see the presentation. I think you should press the start broadcast button to see the presentation if that's missing. Or if nobody sees the presentation, maybe you should give us, you should please write in the chat to make sure you see the presentation now. I can see it, so obviously it's there. 2 weeks ago, we had an issue with Microsoft Edge because Microsoft made an update just before the webinar. So there were some issues, but I think it's solved now. So yeah, people say it works. All right. So Milos, the stage is yours, and I'll be back for the Q&A session in probably 35 to 40 minutes. And just one more comment, maybe you can take the microphone a little bit further away. I think we hear you breathing. Just
is it better now?
Now I think it's perfect.
Okay, I will not change anything. Thank you.
Okay. And no, we will not share the slides themselves. We will make it available on YouTube, Nicholas. So just stay tuned. You can get everything from YouTube probably tomorrow. All right, so I'll be back for the Q&A. Milos, the stage is yours.
David, thank you very much. As David mentioned, this presentation will be available on the YouTube channel, so you will have an opportunity to see and check this presentation again. First of all, ladies and gentlemen, dear colleagues and friends, thank you for your attention. David, thank you for your invitation for this webinar. The title is Hydrogen Embrittlement and Material Selection. And at the beginning, let's just say that when we talk about hydrogen technology and implementation, we must take into account the two important factors. The first one is economy, how to provide the economic way to use hydrogen and hydrogen technology. And the other very important aspect is safety, how to prevent any damages or fracture of components due to interaction between metallic material and hydrogen embrittlement. I will be focused in this webinar about the hydrogen embrittlement and material selection and the effect of hydrogen embrittlement on steels and other metallic material. The webinar will be divided into 6 sessions. First topic is what is hydrogen embrittlement, a brief overview. The second topic is hydrogen embrittlement mechanisms in steel and their synergy. We have a lot of problems. Still, there is no agreement about the hydrogen embrittlement mechanism and their synergy in metallic materials, and we proposed a model, which I will present. The third topic is the effect of hydrogen embrittlement on mechanical property of steel and other metallic material. The third part is very interesting for industrial partners. The problems of hydrogen embrittlement in pipelines transporting hydrogen gas mixture, a hot topic. Session 5, how can hydrogen embrittlement be predicted and avoided? And finally, a summary about materials, hydrogen application, hydrogen embrittlement, and safety. So, The first slide explains the sources of hydrogen, where hydrogen comes. We have two kinds of source of hydrogen. The first one is so-called internal hydrogen, which means that hydrogen enters metal during manufacturing and processing. Various processing techniques like welding, surface chemical cleaning, electroplating, or heat treatment can introduce hydrogen into metal prior or before the actual operation. So we have also a hydrogen in metal as an impurity. The other most important source is so-called external hydrogen, when hydrogen enters metal from the environment. In that case, we have two important and different sources. The first one is so-called gaseous hydrogen at high pressure and temperature, which means that, as you can see on the middle left picture, metal surface is in contact with molecular hydrogen, which then dissociate and form atomic hydrogen, which could enter the metal through a complex multi-step process. The other source of atomic hydrogen which could enter the metal, because molecular cannot enter the metal, is so-called cathodic hydrogen, which is produced as a result of cathodic electrochemical reaction, various corrosion processes on the surface of metal, which as a byproduct have a hydrogen which could easily enter into the metal. As we can see on the middle left picture, we have two sources. The first process is dissociative absorption of molecular gaseous hydrogen, which produce atomic hydrogen, which could enter and be absorbed on the surface by a very complex process. And the other one is corrosion process as a source, second source of external hydrogen, where also atomic hydrogen could enter into the metal. The next four steps explain how the hydrogen materials interaction start. The first process is enrichment of surface layer with hydrogen. The second one is diffusion of hydrogen through metal. And the third is very complex hydrogen materials interaction, which finally leads to the hydrogen damages. And as you can see on the picture, we have typical hydrogen-assisted cracking. As you can see on the slide on the left side, we have a green marked process. The first one is adsorption. The second is absorption into metal, then diffusion of hydrogen, which is controlled by the stress field in material. So we have an accumulation and uneven diffusion through the metal, and accumulation in particular area with a very high hydrogen concentration on typical trapping sites in microstructure. It is important to note that these three processes, A, B, and C, marked in green, adsorption and absorption, but also hydrogen atom generation, as you can see in the down right part of the slide, are different in the case of gaseous hydrogenation of material and cathodic hydrogenation of material. So we have a difference if the source of hydrogen is hydrogen gas or corrosion process. When we talk about hydrogen materials interaction, the important industrial aspect is hydrogen damages. So you can see here on slide in different colors various hydrogen damages. Hydrogen damage is a general term used for all of them, but actually hydrogen embrittlement marked in red is different from other hydrogen damage process, hydrogen-induced cracking or high-temperature hydrogen attack. As you can see, hydrogen damage is one of the major causes of damage and very often catastrophic failure of different engineering components and equipment. What components are affected? Particularly tubes and pipelines in power and oil gas industry, also military aircrafts, all components exposed to seawater, also automotive components are exposed to hydrogen embrittlement. Of course, different part of hydrogen chain, like hydrogen refueling station, pipelines, as I mentioned, also fasteners, and at the end we have hydride embrittlements, which is typical for metallic alloys for nuclear systems, and I will not talk about that. As you can see, almost all structural materials are affected by hydrogen embrittlement and other hydrogen damage mechanisms, like low carbon and low alloy steels, also advanced high-strength steels, martensitic steels, and other grade of steels, but also aluminum alloys, also nickel-based alloys used in seawater and other equipment, and also copper-based alloy. But recently it is confirmed that also a high entropy alloys are very susceptible to hydrogen embrittlement. So a lot of mechanisms and a lot of materials which are prone to hydrogen embrittlement. We need to make the classification of hydrogen damages. As you can see, in the case of steel, we could divide into 4 groups. The first one is hydrogen embrittlement. The second is hydrogen-induced cracking, which is not the same mechanism as hydrogen embrittlement. The third one is hydrogen stress cracking, and high-temperature hydrogen attack. Due to different hydrogen materials interaction, as you can see in the upper right part of the slide, different hydrogen embrittlement mechanism with acronyms AID, HEAD, HESIV, and HELP could appear, very complex mechanism on a nano level. What is the definition of hydrogen embrittlement to make the clear distinction between hydrogen embrittlement and other hydrogen damage mechanisms? Hydrogen embrittlement can be defined as hydrogen-caused deterioration of mechanical property of most metallic materials. So, hydrogen embrittlement is one of the mechanism of hydrogen damage, is the degradation of mechanical property of materials, particularly a loss of ductility and sometimes a loss of tensile strength, but not always, which result in decrease in fracture resistance and decrease in fracture toughness of material, which finally produced subcritical cracking from the presence of dissolved hydrogen and various hydrogen embrittlement mechanisms. It's important to know that also fatigue crack growth rate can increase by over an order of magnitude in steel, and we will talk about this later. As you can see on the down middle part on the slide, we have a different location for hydrogen trapping and hydrogen material interaction sites in steels. On the left side, we have hydrogen at solute. Hydrogen is in different defect of lattice of our material, in 1D defects and 2D defects, like in vacancies, in pre-existing void, or at dislocation. Generally speaking, statistically, we can say that under no stress and after some time, we have, statistically speaking, relatively uniform hydrogen concentration, which is not critical for hydrogen embrittlement. On the right side, you can see that we have a stress marked with sigma. Due to the stress, we have a hydrogen concentration in tensile area of material, high hydrogen concentration, where hydrogen is in different traps, hydrogen traps in our material. Typical traps are participates and their interfaces. Also, hydrogen could be located at phase boundaries, at grain boundaries, at grain triple lines. And as you can see on the right part, hydrogen also could be concentrated at surface cracks, like cracks. So it represents the strong stress concentrator, where we have a strong accumulation of high hydrogen content at the crack tip. And other internal interfaces like pre-existing cracks or voids. When we talk about hydrogen materials interaction, just to make the distinction between hydrogen-assisted cracking, which is primarily related to the degradation of crack propagation resistance, which lead to the failure of the components. On the other hand, from the scientific point of view, hydrogen embrittlement restricts on the perception of precise nature of hydrogen-assisted mechanical degradation. And you have in the upper right part the 3 most important factors for hydrogen embrittlement, which is mechanical, material factors, and environmental factors. Hydrogen embrittlement in steels is still a very hot topic. We have 2 mostly accepted mechanisms presented here. I will talk just briefly about so-called HELP mechanism, hydrogen enhanced localized plasticity. So hydrogen enhanced plasticity in material, not brittleness according to this mechanism. While contrary, on the other side, we have a heat mechanism, hydrogen enhanced decohesion. Let's see a middle left picture which explains help mechanism. We have a very localized plasticity zone at the crack tip because hydrogen promote the enhanced movement of dislocation, which provoked the localized plasticity effect on the crack tip, and as a result we have a void growth and coalescence, and typically due to help mechanism we have a ductile failure due to microvoid coalescence fracture mechanism. Also important is the effects of stress marked at sigma on that diagram. Just briefly about heat mechanism, which is a completely different type of mechanism. We have a high accumulation of hydrogen, which provoke the decohesion, which means that we have a drop in cohesive strength of material due to accumulation of hydrogen at particular trap sites, like particle matrix interface, like some pre-existing void, like grain boundaries. As you can see, hydrogen promote the decohesion of the grain boundaries. These two seemingly opposing mechanism help promoted the enhanced plasticity, while on the other side heat talk about real embrittlement, like in the name of the effects, hydrogen embrittlement of material. These two mechanisms are extremely difficult to detect at the same time, so there are numerous papers which tell us about the help mechanism activity, about the heat mechanism activity, depending on experimental condition and everything else. So, as a summary, activation of particular hydrogen embrittlement mechanism is primarily caused by very complex hydrogen materials interaction shown in the previous slide, and by the processes which are operative at micro and nano level at the crack tip, marked in green, exactly in a fracture process zone. So, help mechanism, on the other side we have a question mark heat mechanism. A group of researchers from University of Belgrade in 2014 and 15 proposed, now widely accepted and highly cited, help plus heat model about the synergistic action of both help and heat mechanism in materials. On the down middle part you can see the diagram which summarizes the help plus heat model. This diagram is published in our critical review paper published in 2019 about the help plus heat model. As you can see, the important is hydrogen concentration. At critical hydrogen concentration, we have a change of mechanism from the help plasticity mediated dominance to heat decohesion. At hydrogen concentration on the local level in material below the critical, which means low or medium hydrogen concentration, we have plasticity mediated fracture modes of material, which means that the local critical hydrogen concentration at the trap site is mediated by hydrogen enhanced plasticity. So we have hydrogen mediated hydrogen plasticity mediated mechanism. Help is not the only one. We have other proposed like aid, like adhesive, and other mechanism, and also help mediated heat, while at a high hydrogen concentration above the critical hydrogen concentration we have a heat dominance, which means that we have opposite effects. We have not enhanced plasticity, but actually hydrogen impeded plasticity, and the activation of heat mechanism, which provoke the cohesion controlled fracture modes and typical brittle failure of components, industrial components, and a sharp drop of mechanical properties. So here is the summary. Also published in our review paper about hydrogen enhanced plasticity mechanism, help, and others about heat, and summary that help plus heat model proposed that simultaneous action of both mechanisms are responsible for hydrogen embrittlement, and the ductile to brittle fraction transition appears at a critical hydrogen concentration, and the dominance of one of the mechanism mostly depend on the hydrogen concentration in material, marked in red on the previous slide, and also important is the material stress rate and also some environmental factors. So, as a summary, our high plus heat model was recently confirmed in various metallic materials by experimental tests and also through computations and simulations. So it is confirmed in various type of steel, as you can see, high strength steel, advanced high strength steel, dual phase steel, low carbon steel. Also it is confirmed in iron, and more recently in nickel-based alloy and aluminum alloys. So the synergistic interplay of hydrogen embrittlement mechanism tell us that some of multiple plasticity-mediated hydrogen embrittlement mechanism, HELP or other, together with heat, are responsible for hydrogen embrittlement, but one of them predominant under the specific condition. So as the summary about the mechanical properties according to our HELP heat model, you can see here that we have a critical hydrogen concentration on x-axis, and we have two cases, the actual hydrogen concentration below or above the critical hydrogen concentration. So as you can see, at reaching the critical hydrogen concentration, we have a ductile to brittle fracture transition and sharp drop of some of micro and nanomechanical properties. And as you can see on the down left microstructure figures, we have a typical pure brittle fracture and a sharp drop of mechanical property characterized by the intergranular and transgranular fracture features and micro cracks when we reached and we have an actual hydrogen concentration above the critical. So the affected mechanical properties are tensile stress, yield stress, but not always. So in some cases there is no big change in tensile stress or yield stress, but ductility are almost always affected, and elasticity, and what is the most important, the crack propagation component, which means the fracture toughness of material sharply drop, which finally provoked the fracture of the component due to activation of the cohesion mechanism. So hydrogen blending into the natural gas grid is the very important industrial topic. So currently, as we can see in the upper middle section, we have more than 70 ongoing projects in Europe related to retrofitting and repurposing infrastructure, gas infrastructure, in order to transport in existing pipelines some mixture of gas with hydrogen. So the affected lines are gathering lines, transmission lines, and also distribution lines, but particularly lines with the high pressure of hydrogen gas mixture. As you can see, natural gas electrolysis and petrochemical industry insist on blending, particularly with methane of hydrogen, in order to provide various hydrogen technology. But as you can see in down part of the slide, we have hydrogen damage mechanism. Down left, we can see a hydrogen natural gas mixture transportation, or 100% hydrogen transportation in existing gas pipeline. And we have three typical hydrogen damage mechanisms. The first one is hydrogen accelerated fatigue crack growth. The other one is hydrogen induced cracking. I will not talk a lot about this mechanism. And hydrogen embrittlement. It is very important, downright picture. It is very important to note the particular problem with aged pipelines with pre-existing corrosion mechanical defects due to long-term operation on the inner pipeline side in contact with hydrogen, which will represent the particular area very prone to both hydrogen embrittlement and hydrogen induced cracking, particularly when we have a typical pressure cycling of gas hydrogen mixture in our pipelines. What about hydrogen blending? A very hot topic. As you can see in the middle of the slide, there is still no harmonization of allowable hydrogen concentration in natural gas in European Union countries. As you can see in the upper left part, we have various allowable volume percentage of gaseous hydrogen, which could be in the mixture from 1% up to 10, and recently 20% of hydrogen which is allowed. As you can see in the down left slide, the various blending concentration are allowed in different European Union countries, and currently we have many demonstration projects presented in a table which are being performed around the world, in UK, in Europe, but also in Australia, United States, in order to check the blending ratio, volume percentage of hydrogen from, let's say, 2% up to the 100% pure hydrogen transportation. So the question mark is how much volume percent of hydrogen is allowed in existing natural gas pipelines, whether it's 1%, A, B, 5%, C, 10%, or even 20%. The answer is it depends on the operating condition and definition of the word allowed. When we talk about materials, here is the slide about pipeline steels and hydrogen embrittlement. As you can see in the down middle section, we have evolution of the strength, processing microstructure of various pipeline steels with time, including low grade, older pipeline steels like X42, X46, X52, up to the very modern high strength steel for pipelines like X80, X90 and other. In a pie diagram on the upper left part, you can see that in European Union various type of various grades of pipeline steel are used in percentage, but almost all are up to X70. So the newest one are still not in use in Europe. As you can see on the diagram, Fowler elongation from different grade material, it is obvious that Fowler elongation drop, which is a measure of the plasticity drop, significantly drop in the case of high strength steel. As you can see, ultimate tensile strength rise with the modern steels, and we have a sharper drop of Fowler elongation in the case of X100 in comparison with the older, more ductile and with lower strength steel like X42 or X52. So, generally speaking, we have an increase in hydrogen embrittlement susceptibility with an increase of field strength, but not always. So it is always very viable to be careful to think that lower grade pipeline steel are not prone to hydrogen embrittlement. Pipeline steel with higher ductility and lower tensile strength. So we will discuss now these two microstructures. It's also important to mention that, for example, in the case of X52, we have a change in microstructure. So in the case of vintage X52, we have a ferrite perlite microstructure, and modern X52 structure is elongated ferrite and acicular ferrite. So we have a different hydrogen solubility due to the difference in microstructure and also the difference in permeability in different grades of pipeline steel, which finally define the hydrogen embrittlement susceptibility of particular type of steel. So, hydrogen blending into natural gas grid and hydrogen embrittlement. The first question on the left, is there a threshold below which hydrogen effect can be ignored? The immediate answer is no, because even 1 bar and 1% in blending mixture of hydrogen reduce fracture resistance of steel. So 1% hydrogen blending is only modestly different than transportation of 100 pure hydrogen transportation. As you can see on the diagram, we have a fracture resistant drop by 50%, even in the case of 1% blending. This is the data for X70 still, and additional but small additional drop when we rise the blending ratio up to 10 or finally 100%. The next question is, what about hydrogen effect on the fatigue crack growth rate? Because pipelines are exposed to pressure cycling and also fatigue. So the immediate answer is that small amounts of hydrogen can have a substantial effects on fatigue. Acceleration of fatigue crack growth rate with only 5% are detected, 5% of hydrogen in mixture, with additional small acceleration with higher content. We can see that on the down middle part of the slide. As you can see, we have the increase in fatigue crack growth rate in comparison to green dots related to N2 for 5, 10, 20, or even 50%. So the decrease of fatigue, increase of fatigue crack growth rate is very similar for different hydrogen blending ratio. As you can see in the upper right section, the same applies for almost all grades of steel. So we have a very similar enhancement of fatigue crack growth rate for various steels like X52 up to X80, so the similar results. So generally hydrogen accelerated fatigue by almost 10 times or higher are due to hydrogen embrittlement effect. The next important question I already mentioned, what about the aged, old gas pipelines in hydrogen embrittlement? The left side of the slide talk about the effects of gas transportation in older pipelines. What about the aged gas pipelines and hydrogen embrittlement? So here we have a results for a drop of mechanical property due to a long-term operation and transportation of gas, not hydrogen or hydrogen mixture in the gas pipelines. As you can see, the plasticity after 30 or 40 years is reduced by almost 42%. But what is the most important, because of long-term operation and slow hydrogenation of material during gas transportation, we have a sharp drop in fracture resistant, particularly crack propagation component of fracture resistant, as you can see on the lower diagram, dropped by almost 40% after 30 years of operation. So the answer is that after long-term operation, plasticity and fracture resistance of aged pipeline, which transport gas, not mixture of gas and hydrogen, sharply decline. The particularly important is the next question in the upper right part of the slide. What about the aged gas pipelines with corrosion mechanical defects? As you can see, gas pipelines almost always have on the inner side pre-existing defects, corrosion defects in the forms of gouge or some crack-like defects or mechanical defects, which have a substantial effect of hydrogen embrittlement. So the answer is that pre-existing corrosion mechanical defects are a strong stress concentrator and strongly enhance hydrogen embrittlement, hydrogen-induced cracking, and also stress corrosion cracking plus hydrogen embrittlement, as you can see on the slide which explain the notch effect. So that kind of defects are notch and stress concentrator. The third question is, what about welded joints of aged gas pipeline? As you can see on the diagram, on the down right part of the slide, we have a very high hydrostatic stress in particular welding area, particularly in weld metal and heterofatty zone, which provoke the accumulation and high hydrogen concentration because of residual stresses and stresses in material. So we have a high hydrogen concentration in welded area. So the answer is that weld area as a strong stress concentrator represents the area with a very high hydrogen concentration and also prone to hydrogen embrittlement, particularly weld metal and heat affected zone. So how can hydrogen embrittlement be predicted and avoided? That's the most important thing for industry. As you can see, we have 1 and 2, and we have 3 and 4. So when we talk about hydrogen embrittlement mechanisms, about atomistic and nanoscale hydrogen embrittlement mechanism, it's very important to note that maintenance engineering and people for industry doesn't care about which hydrogen embrittlement mechanism is effective and active on nanoatomic scale level. They only care whether and when their components will fail due to hydrogen materials interaction, and they need some practical tools. So on the one side, we have a scientific approach, which is the phenomenological research of hydrogen-related degradation. As I previously told, still there is a disagreement about hydrogen embrittlement mechanisms, and we talk about a very complex hydrogen entry into the metal and various hydrogen sources. So scientists investigate 1 and 2, but we need to provide a practical tool for the industrial sector, which means to provide an effective structure integrity model for prediction and preventive maintenance of industrial components exposed to hydrogen. So we need to form structure integrity and predictive maintenance model for industrial application based on the multiple active confirmed hydrogen embrittlement mechanism according to our helpless heat model, connect with the easily measured micromechanical behavior of material, and to define the so-called critical hydrogen concentration for particular application and for particular steel in order to provide predictive, reliable and accurate life damage models and prediction of components like pipelines and other industrial components. So here is my proposition how to do that. What we need in the case of pipelines with some blending ratio or 100% transportation hydrogen pipelines. We definitely need a comprehensive technical and scientific assessment program for retrofitting the natural gas grid for hydrogen transportation. So we will start with the key factors. What is the 3 most important key factors shown in down middle? As previously explained, mechanical, material and environmental factors combination provoked hydrogen embrittlement. So the most important mechanical factor is a global and local stress level, pressure cycling in pipelines, cycling loading, which generally produced fatigue, and as I previously explained, enhanced fatigue due to hydrogen embrittlement. We also need to investigate the presence of stress concentrator like existing corrosion damages in aged pipelines and welds. What about material? Hydrogen embrittlement susceptibility of steel is very important, and it's different for different type of steels depending on the microstructure and numerous other parameters. And an environmental factor is to investigate and determine the global and particularly local hydrogen concentration in steel, and to compare that concentration with so-called critical hydrogen concentration in order to avoid the sharp drop of mechanical property upon activation of heat mechanisms. So what about what we need to do related to pipeline material, operation, integrity assessment and safety? Just briefly, pipeline material points. It's necessary to investigate and correlate pipeline microstructure, old steels, new steels, and hydrogen susceptibility. To investigate further the effects of fatigue on the fracture of pipelines, particularly at high pressure and high stresses. Also, we have numerous cathodic hydrogen charging results, but actually, when we talk about pipelines, we need a gaseous source of hydrogen in order to reveal the true hydrogen embrittlement susceptibility. So these 2 types of results from cathodic charging or gaseous chargings are not comparable. What about aged pipelines and hydrogen blending allowed ratio? Next is welded joints. I already mentioned that. So we need also to develop new pipeline steels with improved hydrogen embrittlement resistance for usage in hydrogen blending and 100% hydrogen transport. We also need to evaluate the plastic pipelines made of polyethylene for hydrogen transport, particularly at lower pressure, and evaluate the hydrogen-assisted fracture of such pipelines. And finally, we need the fundamental research to bridge the knowledge gap in mechanisms of hydrogen embrittlement and the complex hydrogen materials interaction. What about operation? That's the most important for industrial partners. Define the procedure for a repurposing of existing gas pipelines. Define the optimal operating condition for hydrogen blending and 100% hydrogen transport. Defining allowable hydrogen concentration in natural gas depending on the age of pipelines and the material of pipelines. Also define optimal operating condition for hydrogen blending in aged pipelines. And it is also necessary to define improved maintenance practice and strategy for pipelines for future hydrogen transportation. Integrity. We must implement a structural health monitoring system in pipelines for hydrogen transport. The second important thing is inspection and mapping of internal corrosion mechanical damages in all age gas pipeline converted to hydrogen transportation. We can use inline inspection tools for that. We also need to implement model structure integrity assessment and reliability and risk-based models for damage prediction and also for life estimation of hydrogen pipelines, and to develop a structural integrity and predictive model for reliable life prediction, as I already told. Regarding safety, we have standard codes which are old one, so we need to develop the new standardization, particularly for fatigue effect and fatigue crack growth rate in materials, and also there is a conservatism in the test condition according to the current hydrogen standard. So we need also to develop as standardized high pressure gaseous hydrogen charging test methods for experimental investigation of hydrogen susceptibility of pipeline steel. In Europe, there is no lot of equipment for high pressure hydrogen testing. Contrary in the United States of America, there are a lot of efforts led by Sandia National Laboratory and United States energy governmental sector regarding the experiments with high pressure gaseous hydrogenation of material in order to investigate the hydrogen embrittlement susceptibility of particular pipeline steel. So, summary. Hydrogen degrades the mechanical property of most metallic materials. Materials compatibility for hydrogen service depends on the application and the design. Retrofitting and repurposing existing gas infrastructure that allows the injection of a certain amount of hydrogen blending, or repurposing, which means converting existing natural gas pipelines into 100% hydrogen pipelines, is a very hot and interesting topic. But it is widely believed that existing gas pipelines that are retrofitted for transportation of gas hydrogen mixture or repurposed for 100 hydrogen transportation are a viable option and safe for, I will mention that, long-term safety future usage. But, however, despite the fact that the gaseous hydrogen transport via existing gas pipeline is a low-cost option for delivering a large quantity of hydrogen embrittlement, I want to point it out that there is a serious threat of hydrogen damage and catastrophic failure, particularly for old-age gas pipelines, and particularly after future long-term service and transportation of hydrogen in, for example, gas pipelines with pre-existing defects on the inner side. So we need to implement structural integrity model for estimation of safety of such pipelines. A small volume percentage of gaseous hydrogen mixture, you can see only 1% can lead to serious pipeline material degradation and hydrogen embrittlement, which produce the acceleration of fatigue by almost 10 times, while fracture resistance can be reduced by more than 50%, of course, depending on material, stress condition, hydrogen pressure, and hydrogen concentration in steel. So the allowable hydrogen natural blending ratio is not a predefined parameter and depends on the operating condition, depending on the pipeline material, and the most important, on the age and condition of existing gas pipeline, which should be converted to the blending or 100% hydrogen transportation. The lower grade pipeline steel with lower strength and higher ductility, the older one, are not safer per se for hydrogen transportation in comparison to higher strength modern pipeline steel, since they are still very prone to hydrogen embrittlement depending on microstructure and other factors. So there is a need for demonstration project on suitability of both older, low-grade and modern high-grade pipeline steel for use in high-pressure hydrogen transport for long-term with a very high safety in order to provide the reliable exploitation of hydrogen pipelines. And also it is important to investigate the hydrogen embrittlement susceptibility of the old steels in older pipelines. So we need a comprehensive, I presented that, technical scientific assessment program, which must be developed and applied to examine the suitability, integrity, and safety of existing, aged, and new gas pipeline for both hydrogen blending and future 100 hydrogen transportation. As you can see, only 1% could have a substantial effect on mechanical property in the gas mixture. Not a big change when we increase the blending ratio. Aged gas pipelines suffer from deteriorated mechanical property. I will want to point out once again, the most problematic are aged gas pipelines with pre-existing corrosion and mechanical damages, with sometimes very poor quality girt welds, which represent the stress concentrator, which can significantly accelerate hydrogen embrittlement and eventually failure of such pipelines. There is a need for demonstration project on suitability of modern high-strength pipeline steels, also newly developed high-strength pipeline steels with improved hydrogen embrittlement resistance for pure hydrogen transportation. And finally, there are some recent research which indicated the addition of gases such as oxygen and other passivating chemical species can mitigate hydrogen embrittlement in the case of hydrogen transportation in gas pipelines. So thank you for your attention. You can see here on the last slide selected books, and chapters and papers by a group of authors from University of Belgrade, cooperation with some foreign institutes, with Australian partners, and we have a plan for future work with some other European Union partners. And you can see here my email if you need some additional question after this webinar. Thank you very much for your questions. I'm open for question and answer section.
Wow, thank you very, very much, Milos. That was an amazing presentation. But let me be very honest. From my perspective, also very, very challenging to understand. So I think I need some more time to really, to let it sink in and really understand. So I see lots of comments. Excellent presentation. Thank you. Thank you. So to the audience, if you liked it, please write a short comment. I think Milos will be very happy to read positive comments. And if you have more questions, please ask them in the chat section. Let me just take a minute to say thank you to Cummins, to Hexagon Puros, to Nia, to Burkhardt Compression, Drager, MSA, Siemens, ThyssenKrupp, Nucera, Wenger Engineering, MCell, Nito, Phoenix, Contact, and Refire, to our sponsors. Without you guys, this would not be possible. And I think we shared, or Milos actually shared, fantastic knowledge with you today. And yes, I see lots of positive comments. And we said it before, we will publish this video or this webinar on YouTube tomorrow, so you can watch it again in case you missed something. Wow. Okay. So we have lots of questions, and I hope everybody is ready to. All right. So Milos, are you ready for the question?
Yes, I'm ready, David.
Okay. First question, maybe an easy question for you. It's regarding, I think it was slide number 2 or 3. What causes the hydrogen molecule to dissociate at the surface of the metal, or of the let's say the pipeline or of the component?
So it's a very complex phenomena. So we have two processes by which the molecular hydrogen could be converted to the atomic hydrogen. The first one is a spontaneous process, which rarely occurred in pipelines transporting hydrogen. But the very important, I mentioned that process, is so-called dissociative adsorption, which is the process which spontaneously occurred at the inner surface of hydrogen materials. But it's interesting that a group of researchers from Canada, particularly Professor Frank Cheng, work on the way how this process actually happened, and what is the amount of this dissociative absorption process happening on the surface of hydrogen pipelines, in order to define the amount of hydrogen atoms which will be formed because of that process, and eventually which will enter into the metal, as I presented on. So it's depend on numerous factors, like the roughness of the surface, like the kind of fluid flow in pipelines, the regime of fluid flow, and also depends on pressure of gas mixture, depends on the temperature, and depends on the operating parameters. So it is a challenging first question. So we need, for example, additional research into the how dissociative absorption happens, when happens, and what is the precondition, and what amount of hydrogen will be realized and decomposed from gaseous to atomic.
Okay. So I thought it was an easy question for you, but it seems to be very complex. Okay.
No, it's not an easy one.
Okay. One question from someone who was obviously a little bit frustrated by your presentation, who asks, should we use polyethylene pipelines instead? So let's say made from plastic instead of steel, to prevent hydrogen embrittlement. So
okay.
Is steel the best material?
Yeah, absolutely. The problem is with the strength and the price, of course. Recently, there is ongoing research in UK. I think the TVA and some industrial partners are working. There is a strong team in United Kingdom, which work on also the team at Santia National Laboratory in the United States work on that. The problem is that plastic material also have degradation phenomena. It must be investigated. But the problem is the strength level of such materials. So in the case of low pressure, it is possible to implement polyethylene pipelines, but in the case of transmission line with high pressure, there is a problem because not enough strength of such polyethylene. Yes. And also we need to investigate the effects of aging and degradation of polyethylene due to contact with the gas mixture.
I think
there is ongoing research in the world related to that.
Okay, that sounds good, because the next question relates to that as well. What about internal coating of pipelines? Would that help?
Okay, I didn't talk a lot about that. We have two options. We have an option for internal liners, which is particularly some type of composites, and also we can use permeation barrier, which will prevent the enter of hydrogen into material. But it's important to note that application of internal liners, various composites, decrease the hydrogen permeation, but not 100% decrease. So we will still have an entrance of atomic hydrogen into material. And also we must talk about technological challenges, how to apply permeation barrier, particularly for aged old pipelines, not the case for new one, but the older one with the pre-existing cracks and pre-existing corrosion damages. So when we talk about internal liners and permeation barriers, we also talk about economy of such and technological feasibility of such applications. Okay. So it is possible to solve a little bit problem, but not to cure the problem.
Okay, that sounds well. That sounds reasonable. And we have a question regarding liquid hydrogen pipelines. I'm not aware of any liquid. Well, I mean liquid hydrogen pipes, yes, but not pipelines, meaning 100 kilometers, minus 253 degrees. So, what do you think about, or what's your take on liquid hydrogen pipelines, or pipes, or components in general? Are they more prone to hydrogen embrittlement, or is it no big deal at low temperatures? What's your opinion on that?
I think that there are additional problems with liquid hydrogen. Still, there is no exact research related to hydrogenation in that cases. But I think that gaseous hydrogen transportation through existing pipelines is the only viable option. So we could transport by roads in some special pressure vessels and at low temperature. So mostly I think that in the near future transportation will be of gaseous hydrogen, but still there is no enough research data related to the problems of transportation and storage of liquid hydrogen.
Okay.
So we need to investigate that, but from economical point of view, I think it's not a feasible solution for transportation of large amount of hydrogen in the near future.
Yes, I agree. Probably not. The same is probably true in the long-term future, because it's very challenging from physics. So what about the influence of the temperature on hydrogen embrittlement and material resistance, going from plus 100 degrees to minus 254 degrees C? Is it?
We have different effects at low temperature and at high temperature, particularly some type of hydrogen damage mechanisms, which I didn't explain in details in my presentation, are so we can divide hydrogen damage into low temperature hydrogen damage mechanisms and high temperature hydrogen damage mechanisms. So in the case of high temperature hydrogen attack, which is typical for oil and gas industry and a very actual problem, we have a totally different mechanism, which are based on the reaction of hydrogen with carbon for material. So we have chemical reaction and formation of methane within the microstructure, which provoked high pressure effects on grain boundaries and other features in microstructure. Okay. So it's a very similar like hydrogen-induced cracking, which is also very active at about 200 degrees, which is formation of gaseous, the reversible process. So we have the adsorption and dissociation of hydrogen, molecular hydrogen on the surface of pipeline steel into atomic, which enter the metal. And we have a contrary process in the microstructure where two atomic atoms of hydrogen recombined and form molecular gaseous hydrogen, which also have a pressure effect. So that is the hydrogen-induced cracking. Yes. In the literature, you will see the big problems with the definition of particular mechanisms. So when we talk about hydrogen-induced cracking, people think that it's the same like hydrogen embrittlement, but actually it's not. So I will use this question to explain that hydrogen embrittlement is the most typical at ambient temperature, and at very high temperature we have a decrease of hydrogen embrittlement, particularly HELP mechanism is not active. Why?
Okay.
Because there is no way to follow the movement of high dislocation in a material with the atmosphere, collateral atmosphere of hydrogen. At high temperature, the dislocation will move very fast because of increased plasticity, so it will not it will not have a hydrogen catch with dislocation. So there is some kind of decrease of hydrogen embrittlement, and at very high temperature, hydrogen embrittlement is not as active, but we have high temperature hydrogen attack as a different mechanism. So actually the whole temperature from 0 to 500 degrees are covered by hydrogen materials interaction, and also at low temperature we have a sharp drop in ductility of steel combined with hydrogen embrittlement. So the very broad range of temperature are covered by various hydrogen materials interaction and various hydrogen damage mechanisms, as I explained.
Okay, you know, I've been in the hydrogen industry for 18 years and I've never been afraid of hydrogen, but today, you know, okay, so high temperature for you is 300 degrees or 100 degrees or 500 degrees? What is high temperature for you?
When I talk about high temperature hydrogen attack, it's typically occurred at 200 degrees and up.
And more, okay.
Yeah, and the middle temperature is something like 200 to 250.
Okay.
Particularly that process of recombination of atomic hydrogen in the voids and large enough defects in material are intensified at temperature below 200 and 250 degrees. And that's the reason why we have hydrogen-induced cracking during cooling down of welds. So cold cracks in material appears in that range when we have a recombination of atomic hydrogen between 200 and 250 degrees, and at ambient temperature that process is not so active.
Okay, that sounds reasonable. And well, we've got a question which I think.
But just one comment.
Yes.
That recombination of atomic hydrogen and the formation of gaseous hydrogen and hydrogen-induced cracking could appear at ambient temperature if we have a large enough hydrogen accumulation in particular area. Which is large enough to hydrogen molecule be formed in that defects. So we have actually combined hydrogen embrittlement and hydrogen-induced cracking even at a lower temperature below 2000 degrees.
Okay. Wow. Harish, good question. Is there any positive effect or impact from hydrogen onto metals? Any feature that could be turned or looked into for positive considerations?
Yeah, absolutely.
Any studies in that direction?
Yes, absolutely. We must talk about, and there are several papers published about plasticitation, about how to improve the plasticity of hydrogen. As you can see, at the lower hydrogen concentration, hydrogen, due to hydrogen enhanced localized plasticity mechanism, actually provoke the increase of plasticity of metal. So the metal could be more plastic if we done proper experiments and proper saturation of material. So there is a beneficial effects absolutely of hydrogen on mechanical property. As you can see, depending on the hydrogen concentration, we could have an increase in mechanical property at some level of hydrogen in material, but then sudden decrease of mechanical property, and that's the point most important in our HELP plus heat model, because we have two opposite behavior of hydrogen in material. So they could produce the enhanced plasticity of material, which is opposite to the terms hydrogen embrittlement, because embrittlement doesn't mean the increase in plasticity, but actually at low hydrogen concentration, due to very complex hydrogen material interaction, particularly between hydrogen and dislocations, which movements are enhanced when we have an atmosphere, quadrilateral atmosphere of hydrogen with particular edge or some other screw dislocation. But when we increase the hydrogen content, we have an opposite direction. We have a change from enhanced plasticity to impeded plasticity, which means that we have a true embrittlement and brittleness of material above the critical hydrogen concentration. But estimation of critical hydrogen concentration on macro level is not the same as on the micro level. And in our review paper, we explained that actually micro concentration of hydrogen provoked crack propagation. So you can measure with the measurement units the microscopic content of hydrogen, but you are not sure about the actual redistribution. So we have a very uneven distribution of hydrogen in material. So the average content means nothing if we have a supersaturated area with high hydrogen content.
Yes, of course, of course. That was also a question. How do you measure the hydrogen concentration in metals?
There is different methods. One of the most usually used are high temperature gas extraction methods, where we extracted the hydrogen by heating of our specimen, and also we use typically TDS analysis for investigation of diffusible and content of hydrogen, but after enough heating, it's interesting that traps, which I mentioned, the position, location which trap the hydrogen, could be reversible and irreversible. So at some temperature, the hydrogen could be realized for reversible traps, but strong traps are binding hydrogen more with more energy, so it's not easy to measure that type of strong trapped hydrogen material. Actually, we could easily measure the diffusible hydrogen, which could be re-realized from the traps at high temperature. So there is reliable instruments for microscopic measurement of hydrogen content, so-called hydrogen analyzers.
All right. Okay.
Which is automated mechanism, and we have results in ppm, the amount of hydrogen.
Okay. Okay.
Extracted from the specimen.
From the specimen. Okay.
But not from the pipeline.
Of course, which is another challenge, and it might be different. Question from Paul Martin, another person who's very active on LinkedIn, commenting on hydrogen. He was our speaker a few weeks ago. Very good question. Is it fair to summarize that repurposing existing aged natural gas pipelines for use with hydrogen is very risky and should be assumed to be unsafe until proven otherwise?
I will be very cautious with that, since in Europe there is a very few facility which use high temperature hydrogen gas as a source of hydrogenation. So we must say that, for example, United States of America and Australia is a little bit more cautious with that. Actually, the effects of pre-existing corrosion damage could be significant, but let's say that we must use that with cautious, and we must implement the multi-step procedure as I suggested in my presentation. First is to investigate the real corrosion damage level of older pipelines in order to reveal by inspection intelligent tools the distribution and the size of corrosion defects, and then to try to use some of the models which are currently presented in order to, we also work on that models for reliability assessment of pipelines with pre-existing defects and hydrogen together. So we must be cautious at least regarding the safety, particularly after the future long-term exploitation. Maybe problems will not appear immediately, but after some time, as I showed on slide, which mentioned that hydrogenation exists after 30 years of exploitation, even if you have a gas transportation. So a lot of research are done related to the degradation of mechanical property of gas pipelines after the long-term usage.
Okay.
It's also depend on the age and on the condition of particular. If we have particular pipelines which is very old and have problems with leaking already and have corrosion damages, I will be very cautious to put any amount. As you can see, even 1% could be unbeneficial in the mixture in order to provide the safe future exploitation of such pipeline.
A question that I have had, so thank you very much for that explanation. And I've had, that's a question that I've had for a long time, and now I'm going to ask it. I have a paper here. It's in German from 1995 that looks at existing hydrogen pipelines. And this table here shows looks at pipelines, and the longest one we have in Germany was built in 1939, a hydrogen pipeline, 1939. So it's more than 80 years old. It's 200 kilometers long. And this paper, which is almost 25 years old, but it says no damages, no hydrogen damages so far. But it has a safety factor of 4.6, so a very relatively high safety factor. So is it fair to assume that if you have enough safety factor, then you're fine with hydrogen embrittlement because you have enough margin? Is that a fair assumption?
Okay. The generally codes for hydrogen pipelines, actually ASMA B31.12 from United States provide the security by applying the let's say bigger by pipelines which are stronger, which have a bigger just help me
safety factor, or
with safety factor, so we have a larger wall of such pipelines.
Yes, exactly.
So actually the prevention of hydrogen embrittlement are calculated by implementation of a larger pipeline wall. If we talk about pipelines with enough wall thickness and no any mechanical or corrosion damage, we can say that it's relatively safe to use such pipelines. But actually, the problem is structural integrity assessment according to some of the current standards, which have initial flow on the inner side. So we need to define the number of pressure cycle according to ASM B31 standards in order to see after which number of cycles the initial flow will reach the so-called critical flow, which will provide the crack appearance in our pipelines. So everything is about the crack. So if we have a stress concentrator on the outer surface, particularly it's important the contact between the outer surface with the environment and also the contact soil, contact on the outer surface. So we also have a movement. We also have problems of pre-existing cracks on the outer and inner surface of our pipeline. That locations are particularly critical, where we have a pre-existing defects which could provoke as I explained, fracture spreading, the spreading of crack, which could be intensified by hydrogen.
Okay.
So on one side we have perfect pipelines with strong pipelines with enough tube wall thickness, and on the other side we have pipelines with H pipelines with some kind of corrosion defect on both inner and outer side.
Okay.
As I stressed out in my presentation, that H pipeline are particularly important to carefully investigate
before converting them to hydrogen.
Yeah.
Okay.
Absolutely.
So I have, this study, I'm sure you know it, on the European hydrogen backbone. It's updated regularly. And I think it's really a great source of information, and it's really a great study. And, it shows this type of maps, with the green ones are repurposed pipelines and the yellow ones are new pipelines that will be built. And this particular diagram shows, the situation in 2030. There is also one for 2040, which says we will have some, I think, 40,000 kilometers of hydrogen pipelines pretty soon. If you read such a study, from the gas industry, what do you think? Is it realistic? Is more research needed to do that? Is it safe? What's your maybe it's just a feeling, on thousands of kilometers of repurposed pipelines?
That's the reason why I, in my slides, pointed out such a comprehensive technical scientific approach which should be applied.
Okay.
And I give some actual measures what should be done in order to provide the safety is a paramount.
Yes.
So absolutely the failure of gas pipelines is a very strong incident. So
absolutely.
So we can have flames, we can have explosion with hydrogen, we have additional problems. Auxiliary equipment are also need to be repurposed, to be changed, fittings, valves, and everything else. It's not only a problem of pipe material, but generally speaking, I am a big advocate of hydrogen technology. Just to be clear, I believe, and that's the reason why I'm involved in the hydrogen strategy of Serbia. So we believe in green hydrogen, and I'm a believer of hydrogen as a future part of the hydrogen economy. But we must be on the cautious side, and we need to investigate what is the actual problem, David. The first research started in 1892. Professor Johnson published the first paper about the effects of hydrogen on mechanical property. Currently, we still don't have agreement about the true hydrogen materials interaction on various scale. So we have a disproportion of results on atomistic scale up to the going through the mesoscale up to the microscale.
Yes.
So the phenomena on the atomistic and nanoscale are not the same as on the microscale. So hydrogen embrittlement, as you suggested in the intro of question and answer, is extremely challenging topic. Still, there is open question. We could say that we deal with hydrogen embrittlement, but actually we haven't yet agreement about what is exactly hydrogen embrittlement and what is the hydrogen embrittlement effect on all materials. So we have a different behavior and different mechanisms active, for example, in high entropy alloys, for example, in low carbon steels, for example, in high strength steels. You understand? So we have a strong disagreement about results, and I already mentioned almost all the results in Europe are by electrochemical charging of components. So we have experiments when we have electrochemical charging of hydrogen specimen. But actually there is a difference when we have a gaseous and electrochemical facilities for hydrogenation of material. As I mentioned, in the United States, they have a strong equipment for gaseous, which is a pricey equipment. So you need high pressure chambers, you need pipelines, you need to do that. But also the important factor is how to do that, the testing.
Yes, of course.
So we have in situ testing where hydrogen is in contact during the mechanical testing, and we have ex situ testing, and we have a different results. So there is still strong polarization of opinion. That's the reason why this is a hot topic, and so many researchers are involved in this hydrogen embrittlement story.
But it's incredible. I mean, 130 years of research.
Absolutely.
And to be very, very honest, I'm certainly not a material scientist. I'm a systems engineer, but still, I think I have more questions than ever. So it's incredible, and I'm sure we can do a part 2 of that webinar. Just to answer the question that some people have asked, the document is called European Hydrogen Backbone. There's a website where you can download this study. It's, I think, 20 pages or something. Really great study on pipelines. Anyway, so let's go on with the question. We have still lots of questions. Well, Paul, again, that's maybe another question on pipelines. Do you think there is any problem designing new pipelines which will be safe for the users with pure hydrogen? Is that would you say that's easy?
Actually, we have some pipelines produced in Europe or other parts of the world which are certified for transportation and 100% hydrogen. Some companies promoted that pipelines. I have no idea about the hydrogen embrittlement research behind that pipelines, but actually a lot of producers of pipelines are looking forward, are trying to find a way how to produce the let's say steel pipelines with as much as high hydrogen embrittlement resistance. So there is a metallurgical tricks, of course, to optimize the microstructure of such materials in order to be relatively with a high strength but relatively immune to the hydrogen embrittlement. But actually all steels at some level are prone to hydrogen embrittlement. So it is not possible to produce the steel in which there is no hydrogen embrittlement at all. But of course, as I mentioned in on some of the slides, the development of new steels is a pathway how to solve the problem. So we need a new steel material and also to modify the procedure for production of existing X steels in order to provide the highest possible hydrogen embrittlement resistance.
Okay. Okay. Next question. The very good presentation is focused on hydrogen embrittlement for existing pipelines. And how does this relate to new installations using 316L materials? So stainless steel.
Stainless steel, in our review paper, we listed the broad range of steel which are prone to hydrogen embrittlement. So austenitic stainless steel and martensitic stainless steel are also prone to hydrogen embrittlement in not the same level, depending on the conditions, depending on metallurgical factor, depending on the stress factors, as we believe the stainless steel are not prone to corrosion. Yes, they are. There are specific stress corrosion cracking mechanism which are active only in stainless steel. So we published 20 years ago with my mentor and professor Vera Šijački-Žeročić a paper about how stainless steel is actually prone to corrosion. While we believe that with a high amount of chromium and other alloying element, we solve the problem of corrosion. So yes, stainless steel, and as you can see in the literature, there are a lot of paper which investigate hydrogen embrittlement of particular type of material. Almost all type of steel, including recently the hydrogen embrittlement of high entropy alloys. So they are also prone. So generally speaking, when we have a high strength, when we have an improved microstructure, when we have a precipitated hardening mechanisms which improve the mechanical and thermal property of material, we have a higher susceptibility because we have additional traps, grain boundaries, different phases, hard phases in material. As you know, martensite is more prone to hydrogen embrittlement than ferrite, but it provides a high hardness, it provides a high strength of material. So high specification steels and high specification materials are more prone to hydrogen embrittlement. But as I mentioned, we shouldn't believe that low carbon steel with a high ductility is not prone to hydrogen embrittlement. Yes, it is. I mostly work when we propose our Hell plus Heat model on low carbon steel for pipelines. Nothing special. It's a ductile steel with ferrite perlite structure, like X52 old one, which I showed.
Yeah, okay.
And they are prone to hydrogen embrittlement and also high temperature hydrogen tech, particularly at high temperature in pipelines, in boiler tubing system.
Well, but you know, I fear that the people who have attended today will look for a new job now because you know, James, the person who asked the question, works for Schwer Fittings, who will be one of our showroom hosts at Hydrogen Online Conference. So you will be able to meet him, and hopefully he will have some answers regarding his fittings by then, because everybody will ask him, what about hydrogen embrittlement? And obviously these fittings are made from stainless steel, and our friend Gary from Parker made a comment like, very complex topic, don't worry about it, just buy our components and you're fine. So to everybody who if in the unlikely event you haven't registered yet for a Hydrogen Online Conference, please do it now. It's free. It's 24 hours. You will get you know, 30 great presentations, and you will have the possibility to meet lots of great companies who are actually active in the hydrogen sector and talk about their components, their products, and also their services. And you can ask them their opinion on hydrogen embrittlement, and maybe they have a good answer. Otherwise, you know who to talk to from today on. All right, let's go on with a few questions. Do you have a few more minutes?
Absolutely.
It's already, you know, we have.
I'm ready. I'm ready to answer all questions. It is my pleasure.
Okay. How does the pressure affect the hydrogen embrittlement? More pressure, more embrittlement?
I show some results, but almost all results are the results from United States, where they have a established facility for investigation of different pressures. So as I show, even the one bar produce the drop in fracture resistance of material, and with an increase of hydrogen pressure, there is no a big additional drop of fracture resistance. So generally speaking, external loading and condition like defects will likely dominate overall risk. So as you can see, the blending ratio is not the principal concern. So with a relatively low amount of hydrogen, we still have a problem. And also at a relatively low, that's the reason why I a little bit afraid, because when you have a 1 or 2% blending ratio, still the hydrogen embrittlement problems exist. And there is not a strong change in the behavior of material if you increase pipeline pressure or increase the content.
Okay. And would ammonia as a hydrogen carrier have the same embrittlement issues than pure hydrogen?
No. So we mixed different gases with hydrogen, but actually only hydrogen produced such a large embrittlement effect.
Okay, that's a good and promising answer. Does moisture content enhance hydrogen embrittlement? Probably the answer is no as well.
As I mentioned, there is currently ongoing research. I am also involved in Australia in one research related to some kind of gases which could prevent the entrance and intro of hydrogen into material, as I show on the second slide. So oxygen could be used, but still we need more research in order to reveal the effects of gases which could be from moisture on the retardation of dissociation process, dissociative absorption process, which I already mentioned, and also adsorption and absorption of hydrogen into the metal. So on the enter side, to prevent hydrogen to get into the metal. That's the one of the option.
Okay.
Absolutely, but the problem is when we have a high temperature and when we have a high pressure and when we have a transmission line, for example, the big pipelines, how to do that in economic way, how to apply some permeation barrier or some internal liners or coatings or something like that.
Yeah, okay. And you said in your presentation that a little bit of oxygen might even help.
Yeah.
Is there some concentration threshold where this effect starts or where it stops? Or?
Absolutely, it's a brand new research, and it is done in United States of America. I mentioned Santia National Laboratory. They work on that, and there are some already published results. You can check the United States governmental site related to energy. They have some published results, and they have ongoing project related to hydrogen embrittlement of pipelines. Mm-hmm. So as I previously mentioned, it's very important to provide the close connection between industry and between research center and scientists. From my point of view, currently there is not strong enough bounding between these two sectors in order to provide a true breakthrough and to provide pure safety of future hydrogen technology.
I completely agree, especially in Europe. We do a lot of research on fuel cells, for example, on catalysts for fuel cells, which is good. But we don't, I'm not aware of many institutes that work on high pressure hydrogen, for example, not only embrittlement, but also sealings, O-rings, interactions with that, for example. That's something that it's also in Japan, they also do very good research in that field. Europe is...
Yes, I have a contact with hydrogen embrittlement researcher all around Europe, and I'm also for Europe. I'm from Serbia. So I think that it's very important we have a strong team in Germany, in Norway, in France, in other European Union countries involved in hydrogen embrittlement. But I think that a little bit more cautious are United States of America and also Japan and Australia. So in order to promote and to be the leader European Union countries in future hydrogen technology, which is in intention by different governments of different countries in Europe, which I applaud, which is a good idea, we need to collaborate and to work together in order to bring the puzzle. There are different centers. I mentioned Max Planck Institute is very strong in hydrogen embrittlement research. Professor Dirk Rabe group. We have a strong group in Norway. I know them all personally, but there is not enough cooperation because the experimentation related to hydrogen embrittlement are a top material science, and we need a top equipment. And we need a very fine on the lower scale microstructure characterization. So we need very pricey equipment in order to provide the true results. And also, I insist in our papers, we always try to provide let's say, practical industrial model. That's the reason why we scientists work on hydrogen embrittlement. We need to provide to industry some useful tools in order to predict hydrogen embrittlement. And that's the reason why our papers are very interesting and highly cited, because we always try to provide the connection, because our groups also work with industry partners in Serbia and abroad. So we are always thinking about what industry need.
Yes.
They don't care about hydrogen embrittlement mechanism. It's a hard science for them. They need a practical tools, they need a maintenance program, they need a structure integrity analysis, they need inline inspection techniques, which will provide the safety operation of components, no failure, no accidents, no leakage, no anything which will interrupt the production and endanger the economic aspect of production.
Yes, I agree. 100%. So definitely, I'm definitely with you that this is something that has been neglected, and that's definitely needed, whether it's for drivetrains or for hydrogen storage systems or for compressors, for example. I mean, the same mechanisms. I mean, especially in compressors, you have pressure going up and down all the time. You have moving parts. You have various mechanisms simply coming from the mechanics, and we definitely have to look at that. Yeah. So, from your point of view, which would the best steel be in terms of hydrogen embrittlement resistance, considering the microstructure and the mechanical resistance?
It's a $1 million question.
Or even more.
Yeah, believe me, it's very hard to say. Why? As I mentioned, we have three factors: material, stress, and environmental factor. So depending on factors, we have an optimal material for a particular application. And that's the reason why it's not so easy to develop and to make a project. So we must pick up the right material for right application.
Yes.
So there is no the broad answer. It's also interesting to note that there is intention in the European Union to open the hydrogen bank or something like that recently. So a lot of investment will be in hydrogen technology. From my point of view, I am from Western Balkan countries. Serbia is still not a part of European Union, but as a little advice, it is very important to provide funding for additional research related to some of the open questions, which I opened in this presentation, in the future investment, because it will be money for project how to implement as soon as possible hydrogen transition and hydrogen society in Europe, which I applaud and which is very important, particularly having in mind the problems with energy recently all around the world, not only in Europe.
I'm 100% with you, and we'll check afterwards if we had people from the European Union or from the European Hydrogen Backbone Initiative in our webinar. I think we had seen someone from Uniper. So there are people who are definitely dealing with the effect of that in the practical, let's say in the industry. And we'll see if we can contact them or, try to make them more aware of the need.
Yeah, when I talk about hydrogen strategy of Serbia, I always pointed out it's a connection between government, industry, and science.
Yes.
Without the true connection between these three partners, there is no true breakthrough. So we need also on the governmental level understanding of problems, and government must push such things in order to be a good job and good story in the future.
Absolutely. So let's I'm 100% with you. So let's do three more questions.
Okay.
Some.
Sorry, just to drink a little bit water.
Please, please, please. So I can invite our attendees. Let me check how many we have. Okay, we've already lost some, but we had some 2,500 attendees today, which is great. So in case you haven't registered yet, next week we'll talk about hydrogen distribution, not via pipeline, but via trailers and road transportation systems, and also maybe rail cars. We'll see. And we'll talk about mobile refueling stations. In 2 weeks, we'll talk about the total cost of ownership of fuel cell trucks. So will hydrogen be a fuel for the trucking industry? That's what we're going to talk about in 2 weeks. Very interesting white paper has been published recently. H2 Accelerate is a consortium made by Daimler Truck, Iveco, Volvo Truck, Shell, and Total Energy. I hope I didn't miss any one of the participants. So very, very interesting as well. Please register. Okay, so you're back. What about to reduce the stress at weld joints? What do you think, or do you think we should use butt weld instead of socket welding?
The recent results, again, from United States show that there is no big deal with the welds which are properly made.
Okay.
The welds, the new one, and if you use the welding procedure and process with low hydrogen consumable and low hydrogen entry, so there is no problem even with the stress concentrator. But we must recheck the old welds, particularly defective girt welds on pipelines, eventually for the pre-existing, of course, again, of some corrosion defects or some defects at the root side, particularly with some defects in geometry, which could provoke the initiation of corrosion damage, typically in gas pipelines, but also in boiler pipelines when we have a two-phase fluid flow or gas flow at higher temperature. So the results show that potentially welds are more prone to hydrogen embrittlement, but actually there is no problem if the welding is done well.
Okay, that's
with the conventional welding technology.
Yeah. Okay. So that's a very promising. That's very promising. So if and I think even without being, let's say, a material scientist, I think it makes a lot of sense before you fill a pipeline with hydrogen that you inspect it and make sure that everything's fine. Okay, so yeah,
sound reasonably.
Absolutely, and I think that makes a lot of sense. And okay, I'm going to answer the next question myself. How is the industry dealing right now with hydrogen embrittlement with storage tanks and compressors at ambient temperature? So, Davey, I think I have a proposal for you. Just register for Hydrogen Online Conference. You will be able to meet 10,000 participants and other experts in the showrooms of these companies, hosted by these companies and institutes. where you can discuss this question with companies that deal with that on a daily basis, and with other participants that show up. So you will be part of some 50, or you can be part of some 50 web conferences where you can ask any question you have, and anyone who feels like he knows, or he or she knows the answer, can discuss that with you. So in case you haven't registered yet, it's free, and you should do it now. All right.
David, I have one question. I see
yes,
that
please.
There are a lot of questions. Could you please copy to me this session questions?
Yes, of course.
And send me by email. As I mentioned, I'm ready to help and to give additional explanation by email. No problem, because I think that question from industrial partners are the most important one in order to solve the problems and to bring closer to each other. That's
I'm perfectly fine with that. So I think if you want to, we can do some more questions. I'm happy. I told my wife that I sleep in my own bed tonight, so I have a few more hours. So I'm fine with that. But you know, we start to lose people in Japan and Australia and Malaysia, because it's really tough.
Maybe it's a good idea. I could answer to that people by email.
but maybe we can agree that I mean, you're also very active on LinkedIn. Maybe you can try to answer some questions on LinkedIn, so other people can see the answer too. So it's not only, you know, a one-on-one communication, and so people, you know, can find the answers afterwards,
yes.
So I would be very happy. That would be great. So yes, I would.
Please send me the list of questions.
Yes, we will definitely do that.
Yeah, prepare me the documents. I haven't time to check on the right side the people comments, so I didn't read the comments of people because many of that people I know personally. So some of them, of course.
Yeah, the usual suspects.
Yeah.
All right, so let's do some more questions. How much more time do you think we will need to investigate hydrogen metal embrittlement topics before we can begin the wide-scale safe use of hydrogen for the energy transition? And don't tell me it's another 130 years. We must be faster.
Yes. I must tell you something. In recent 10 or 15 years, there is a true breakthrough in understanding of hydrogen embrittlement mechanisms. What is the most important thing? I haven't time to mention that. We have experimental results and we have modeling results. Recently, for example, our helpless heat model are modeled by a group of researchers from Norway, and also there are other researchers from UK which work on modeling approach. So now we are much closer. In order to provide a real breakthrough, we need atomistic and lower scale modeling approach, mesoscale modeling, and also experimental research. So different teams in Europe, and we have conferences very frequently. Let's say hydrogen embrittlement community are very active in currently. So we have researchers from United States, from Australia, from Norway, from Germany, from France, from China recently. I believe that let's say in 5 to 10 years we will provide a true breakthrough, because a lot of money is invested in prestigious material science research related to hydrogen embrittlement, and the number of papers and research projects related to hydrogen embrittlement increasing each year. So I think that we are on the right track, and relatively soon we will find some practical solution. Currently we have some models which are working with parameter fitting and everything else for particular components, but still no practical applicable model for prediction of hydrogen embrittlement in whole industrial sector. There is a recent breakthrough because of improvements of modeling approach and particularly hydrogen mapping techniques at Max Planck Institute in Japan and in America provide some better understanding of where is actually hydrogen in material, because we are not sure where is actually how they move through material. Because it's so small, you understand. We need an advanced microstructural mapping and characterization technique, which are very costly and could be provided by leader countries from Europe and prestigious country with a lot of investment. So hydrogen embrittlement is a topic for a country with a lot of money.
Okay, but can we agree on the following? Just to be very clear on that. We shouldn't delay our efforts to make green hydrogen happen just because, we don't have that model yet. I think we should really go on with our efforts to decarbonize the industry, because I can already see, the comments on LinkedIn. Well, we would do it, but there was this professor from Serbia who told us that we can't because they don't have the model yet. I think we really should move on. And
my answer, once again, I'm a big advocate of hydrogen technology, and we must move in that direction. Okay. This presentation was just my efforts to give some hints, but not to give a complete story. What should be done in order to bring a little bit more safety.
Yes.
As some kind of recommendation for industrial partners. But actually, it is important to provide additional project and to carefully investigate the particular application in order to provide the very high safety, which is a paramount when we talk about hydrogen technology. So go further with everything is my general recommendation, but please be aware of potential problems. That's all.
Absolutely. And I just saw a comment. Thank you for this opportunity of having a great researcher and scientist just for free, with I think 6 exclamation marks. So yes, you're welcome, and we're really happy to do that. And the only thing we ask you is to share the link with your friends, to comment on LinkedIn, to press like, whatever. So to spread the word and to share it with the colleagues.
I must tell you something. I'm very active on scientific network, on ResearchGate. We have a project, Hydrogen Embrittlement Understanding. I also, as you mentioned, have a project on LinkedIn, Hydrogen Embrittlement. I'm active also on Twitter. I haven't mentioned that references because this is a technical scientific presentation. You have my email, but my presence are very well known among the hydrogen embrittlement researcher on all major media, on ResearchGate, on academia, edu, and on LinkedIn, on Twitter. So please follow me and we can discuss. I'm also involved in sharing of researcher by my colleagues and friends all around the world. When they publish some paper, I reshare that paper related to hydrogen embrittlement. So I invite you to join the community. As David and I'm very active like you.
Yeah, that's definitely the only thing I think that you and I really request, or that we want. And everything or what we do wouldn't be possible without companies like Cummins, like Hexagon Purus, like NIA, like Burkhardt Compression, Drager, MSA, Siemens, ThyssenKrupp, Nucera, Wenger Engineering, MCell, Nito, Phoenix Contact, and Refire, our sponsors. So thank you to all of them. And if you want to be a sponsor as well, and be part of our constant efforts to promote the webinars, we have some 50,000 people get our emails 3 times a week. We have I think I have some 40,000 very good friends on LinkedIn. And I think we really promote our sponsors, and all of them tell me that they made a significant amount of money, or they get requests from the industry for their products. So if you want to sell something to the hydrogen industry, I think you should contact us and become a sponsor. All right. So let's
I have just
Yes.
one comment. I see
Please.
one very interesting and funny question. What is the correct spelling of the name of the speaker? So as you can see, I have an international name, which is MILOSDGUKIC. So my actual name is Milos. Sh is at the end. Milos Djukic. So DJ is something like J, and the C on the end is the Ch. So my name is Milos Djukic, the correct spelling. And you spell my name very well.
So thank you very much for that.
I was fascinated when you tell Milos Djukic. So
okay. It's well. I try to be, yeah. Thank you very much for that. So let's see what we can do. Do you work with the Center for Hydrogen Safety in the US? It's a global-oriented non-profit dedicated to promoting hydrogen safety. AICHE. Center for Hydrogen Safety. Do you work with them?
No, I haven't contact with that. I have some contact with people from Santia National Laboratory and the most important project related to hydrogen embrittlement for DO, Department of Energy. They work together with Santia, but with this institution you mentioned, no, not yet.
Okay, not yet. Okay. Do you think that artificial intelligence could help you in some way? For monitoring, for example.
Absolutely, yes. We recently published a paper in Journal of Natural Gas and Technology, a review paper about the external corrosion of pipelines, in which we'll summarize the advanced techniques. So there is a lot of, when you ask me when the hydrogen embrittlement will be solved, I mentioned the advanced techniques. So artificial intelligence and also other methods, advanced modeling techniques, computational modeling techniques could bring a real benefit to the prediction and structure integrity assessment of pipeline corroded on the external surface and on the internal surface. So yes, I believe there are a lot of papers, and we also prepared a special issue. I was a guest editor in a Journal of Gas Technology and Engineering, where we have some new breakthrough papers related to modeling.
Okay, so if you, let's say, if people, let me repeat that again, we will upload this webinar to YouTube, since we believe it's really important, and so people can have a close look at your list of recent publications. And I would assume that if they read these papers, they will be, if they read the reference list and go on, and so they will.
On the list, we have 2 review papers, and in the near future, I prepare with international team another review paper. So you have 2 review papers for 2016 and 2019, which is also industry oriented with some modeling approach, which we provide for our power industry sector. Mm-hmm. So you have numerous references in that papers, and these papers on the list are strictly related to hydrogen embrittlement.
Okay.
But as I mentioned, I also published with people from Algeria and with people from Australia, with a group of researchers together, some recent paper related to oil and gas sector particularly, which is not listed on this list.
Okay.
But it's always easy to check my record and my publication on Scopus, on ResearchGate. Just enter Milos Djukic, but always my international name, not with J and Ch, as I am presented here. And you can find the papers, and I'm ready to send the paper if you haven't access to the database, as I already did numerous times to people from industry. It's always my pleasure to help and also to provide consulting service for people from industry related to hydrogen embrittlement problem.
That's a very good, another very important and very good comment. So let's do just one last question. I think we are a little bit exhausted, or the audience will be exhausted as well. I think, I don't know if that question is ironic or not. Have you considered working or collaborating with Elon Musk from Tesla?
Well, I highly respect people with a vision. So I believe that the vision is the most important. You will always have an opponent when you have a vision.
Yes.
They will always push you down. But I believe in strong leadership, and I believe in people with vision. And I also could tell that your website is one big vision related to hydrogen technology, and it is a real pleasure to be involved in this. And I hope that we will cooperate in near future related to everything, because knowledge is an imperative. Absolutely. And knowledge should be for free. It's my obligation as a full professor to share the knowledge. That's my way of thinking. And young colleagues of mine, not only from Serbia, but from other countries, believe in my vision. And my vision is to provide the safe hydrogen technology without hydrogen embrittlement. I'm working on that for more than 20 years.
What a beautiful last statement. And I believe in sharing free knowledge as well, and that's why we do this, and that's why we had like 2,500 something people on today's webinar, which is amazing, really amazing. So thank you very, very much for everybody. And if you haven't registered yet, register for Hydrogen Online Conference. Free hydrogen knowledge, 24 hours non-stop, and you will get great presentations, and you will have the opportunity to discuss your specific questions regarding your projects with these companies. If you want to be one of the hosts, one of the experts to share your knowledge of your company, please get a showroom, contact us. It's not for that one's not for free, but it's not expensive either. So please register, and see you next week on hydrogen distribution. Please register for free, join us for free, and share the link with your friends and colleagues. So, Professor Milos Djukic from the University of Belgrade. Fantastic presentation, fantastic Q&A session. Thank you very, very much for your contribution to the hydrogen industry. Thank you very, very much for your presentation today. It will be a pleasure to cooperate with you and to do hydrogen embrittlement part 2 anytime in the near future. Thank you very much. Have a nice evening to everybody. Have a nice rest of your day. If you live in North or South America, have a good night if you're in Asia, and see you next week.
Thank you once again to all, particularly to you, David.
Thank you very, very much.
Bye-bye.
Bye.